For today's lesson, we're going to dive a little bit further into what some of the chemical properties are of acids and bases. And as a result of some of these chemical properties, we're going to kind of discover that there may be some different ways to think about acids and bases than what we have come to understand so far. Okay, so per our last lesson, acids produce the hydrogen ion and bases produce the hydroxide ion. We know how to calculate pH with the concentrations of these ions. All good and fun, right? Acids produce hydrogen and bases produce hydroxide sometimes, okay? There are actually other theories on how to define acids and bases. What that means is here are the three main theories on how to define what an acid and a base is. There's the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory of an acid and base. So let's kind of talk about what is going on with these theories. So acids produce hydrogen ion, bases produce hydroxide. This is technically the Arrhenius theory for how to define an acid and base. However, the more we learned about how acids and bases behave, the more we discovered that this Arrhenius theory wasn't the case for all acids and bases. Therefore, we had to kind of expand the definitions for acids and bases to be more comprehensive. So as a result of that, this led to the Bronsted-Lowry theory, which provided a little bit more clarification, and then later the Lewis theory of acids and bases. So let's kind of look at the first two of these theories. The Arrhenius theory, you guys, Arrhenius acids, they are substances that contain hydrogen and produce the hydrogen ion in aqueous solution. So an example of an Arrhenius acid would be hydrochloric acid. We know it is a strong acid. It dissociates completely and produces the hydrogen ion and the chloride ion. Y'all, that Arrhenius acid is totally the acid understanding that we've been coming to the table so far. Well, what does it say about a base? An Arrhenius base is a substance that contains the hydroxide and produces the hydroxide ion in aqueous solution. So here's my strong base, sodium hydroxide. It dissociates completely into the sodium ion and the hydroxide ion. So all this to say that the understanding of what makes an acid and what makes a base that we learned last time was the Arrhenius theory, okay? But Bronsted-Lowry came in a little bit later and he was like, I have some questions. So the Arrhenius theory does not include substances that have basic properties but don't contain the hydroxide ion. I mentioned last lesson, this guy right here, NH3, ammonia, he's a base. And y'all were like, but he does not have hydroxide. I agree with you. So Bronsted-Lowry was confused by this too. So Bronsted-Lowry theory further defines acids and bases in terms of giving or receiving the hydrogen ion, which I will refer to as a proton. You're right, what a proton. Okay, you guys, hydrogen, we know it's atomic number 1, which means it has 1 proton in its nucleus, right? It also has 1 electron for a neutral hydrogen atom spiraling around the nucleus, okay? The hydrogen ion is positive. That means it has gotten rid of that negative electron to where the only thing left is the proton of the hydrogen atom. So a hydrogen ion is literally actually a proton. Okay, so what did Bronsted-Lowry say about acids and bases? So Bronsted-Lowry acid is a substance that donates the hydrogen ion, or it is a proton donor. Okay, so for example, I have hydrofluoric acid. Notice that hydrofluoric acid has a double-headed arrow for his dissociation. That's because he is weak, okay? Here, hydrofluoric acid, it is, when it dissociates, even if it's a little bit, it is donating or giving up its hydrogen ion. So that is an example of a Bronsted-Lowry acid. It's also an example of an Arrhenius acid. So some of the times there's some overlap here, okay? So hydrofluoric acid is an acid. And we see that because he is donating H+, okay? Now a Bronsted-Lowry base, this is where it gets a little bit freaky, okay? It is a substance that accepts the hydrogen ion, or it is a proton acceptor. So what this means is, here's an example. I have ammonia, NH3, and looks like he's been given a hydrogen ion or a proton, and he now turns into this business, okay? Looking at this, ammonia is a base because it has accepted the hydrogen ion or that proton. So this is Bronsted-Lowry's theory, okay? Acids donate hydrogen, bases accept the hydrogen ion. Okay, so what this leads into is this concept called conjugate acid-base reactions, okay? So the Bronsted-Lowry theory requires a second substance for the acid or base in the solution to interact with. In other words, y'all, there needs to be a substance that accepts that hydrogen ion that this hydrofluoric acid is donating. Like, it cannot just go off into outer space. Somebody's got to take in that proton, right? Or also there needs to be a substance that donates the proton to the base, okay? It cannot just come from nowhere. So in each one of these reactions, I need an acid to donate a proton and I need a base to accept it, okay? These reactions are called conjugate acid-base reactions, and they rely on the Bronsted theory of acids and bases. So looking at here, this is kind of a skeleton of what a conjugate acid-base reaction looks like, okay? My reactants are an acid plus a base, and it leads to, or they turn into, a conjugate acid and a conjugate base. If you'll notice, oftentimes these reactions are reversible because these reactions tend to create equilibrium systems, which, don't worry, we're not going to get into for today's lesson. Okay, the way I think about this, since Bronsted-Lowry acids and bases are all about tossing a proton around, donating a proton or accepting it, y'all, it's kind of like a game of pass the proton. Okay, so I have a picture, and I will keep referring to this picture cartoon because it is very helpful for me. Okay, let's say this guy right here, he is holding a proton, yes? Well, he's the acid, okay? And this girl right here, she does not have the proton. She's the base. Okay, through the course of this reaction, the hydrogen ion or the proton gets donated now to the girl, okay? So whoever has the proton on each side of the reaction, we would call them an acid. So on the reactant side here, the original acid, he is the acid, he donates it, and then the girl has it on the product side. So we call her a conjugate acid. Very cool. Okay, so we can define now what a conjugate acid and a conjugate base are by seeing, well, what has happened with this transfer of that proton. A conjugate base, which means this dude right here on the product side of the reaction, is the substance that results after the acid donates the proton, okay? So over here, he was the acid, he got rid of his proton, he has turned into a conjugate base. Acids turn into conjugate bases. That substance that was originally the acid still is the same substance on the product side, just without now a proton, okay? The guy is still the guy on the opposite end, but now he just does not have the proton in his hand anymore. So let's look at this in chemistry because we're not just looking at like people in the world, okay? So here I have a chemical reaction. I have hydrofluoric acid plus water leads to the hydronium ion plus the fluoride ion. Okay, if I'm looking at this reaction, I see that the hydrofluoric acid, he is going to donate a proton to water. And as a result of that, I'm going to see the effect of that on the other side. After he has donated the proton to water, what does he turn into? Well, hopefully the guy that has fluorine in him that does not have the hydrogen ion anymore, yes, this is what he turns into. He turns into the fluoride ion. So the way that we can think about this is hydrofluoric acid is the acid in this reaction. Well, the acid turns into, meaning on the product side, what does he now look like after he has donated his proton? The fluoride ion, which means that is the conjugate base. Okay, you guys, one thing to keep in mind, it is not just kicking off a hydrogen. It is a hydrogen ion with a positive charge. So not only am I removing a hydrogen for him to turn into his conjugate base, I am adding a positive charge or removing a positive charge from that substance, okay? So here hydrofluoric acid started off as neutral. So if I've removed one positive charge, the result will be a negative charge, okay? So you kind of have to think about the charges, which makes it super fun. So now let's look at the other side of this, okay? What is going on with the base, the person who accepts the proton? Well, this is where we get into conjugate acids. A conjugate acid is the substance that results after a base accepts the proton. So over here, we've got our girl, right? We have established that she is accepting that proton from the acid guy, right? But as a result of that, she now turns into somebody different. She is the same girl, but she is now holding that proton. If she's got the proton, then she's the acid on the product side, okay? so bases will turn into conjugate acids. Keeping in mind that the only difference between the base and the conjugate acid that it turns into is just the addition of one proton. Okay, so let's look at an example of this. If I'm looking at this chemical reaction equation, I've got ammonia plus water leads to the hydroxide ion, and oh my gosh, you guys, this is our polyatomic ion friend, ammonium. Very cool. So what I'm looking at here is that NH3 ammonia is actually accepting a proton from water. Well, as a result of that, what does he turn into? Oh my gosh, he turns into the ammonium ion. Noticing the difference between NH3 and NH4 plus is I've added an extra hydrogen, but also that hydrogen proton comes with a positive one charge. So he was neutral and now he ended up positive, okay? So that means since he has accepted a proton from water, he is the base. And then NH4 plus is its conjugate acid. So once again, bases turn into conjugate acids, which is very exciting. Here we go though. Did you maybe notice that for each one of these two example reactions that we did, there was an acid and yes, it turned into a conjugate base, but there was also a base guy, somebody who had to accept that proton that that acid donated. And we know bases, it was going to turn into a conjugate acid. Yeah, so for our first example where we stated that hydrofluoric acid turned into the conjugate base of the fluoride ion, well, he donated his proton to water. Hello, base water, right? Because I've accepted a proton. And then that water had turned into the hydronium ion. So that base turned into a conjugate acid. Once again, acids turn into conjugate bases. Bases turn into conjugate acids. In our second example, same thing. Yes, we said ammonia. He is a base because he accepted a proton, which means that base turned into the conjugate acid, the ammonium ion. But you guys, he accepted that proton from water. So that water is the acid involved in this chemical reaction. And what water turned into, the hydroxide ion, is the conjugate base. Amazing, okay? And one thing to keep in mind that I'm looking at, which is why I've circled these hydrogen protons, is whoever has that proton on their side of the equation is the acid, okay? Whether on the reactant side, it is the starting acid, or on the product side, it is the conjugate acid. Okay, let's do some practice. So now that we've established this, I'm gonna give you some chemical reaction equations, and we're gonna identify who is the acid and who is the base on the reactant side, and then who is the conjugate acid and the conjugate base for each reactant. And you were like, what am I even supposed to be looking at here? You guys, this is just somebody over here is the guy, somebody over here is the girl, and then over here on the product side, somebody is the guy and somebody is the girl. The only difference is that the proton will have been passed from one to another. So the way that I handle these is I look at both sides of the reaction equation kind of together. I'm like, all right, here's my reactant guys before the transfer of the proton in some way. And my product guys over here, those are the same people, except I'm looking for who has changed in what way depending on that proton transfer. So what I'm actually looking at is, oh, this catches my eye. This HSO4 minus, and y'all, I see the OSO4 minus too. That looks like there's a little bit of a difference. That gives me some orientation to know how I'm going to proceed forward, okay? That means that he has lost in some way that hydrogen proton to turn into that. Well, if he has lost it, that means he must have given it to water. And do we, in fact, see that change represented with the water? Yes, on the other side. Okay, so we've figured out what the proton situation is from where it started with and where it is ending to. So what we have here is HSO4 minus is going to donate its proton to water, right? So we've got an acid established and we've got our base established. Well, what happens as a result of that? Who do I label? Who do I label? Acids turn into conjugate bases and bases turn into conjugate acids. So that means my acid turns into this conjugate base over here, and my base, which was water, turns into the conjugate acid. Noticing that whoever has the proton on both sides is my acid. Amazing. Okay, here we go. Another one. So you're like, oh my gosh, what is happening? All right, so here are my players before the proton transfer. Here are my players after the proton transfer. So what am I looking at here? What am I looking at here? I see this business looks kind of like one dude, and this is the same dude on the other side. The difference being, oh, a difference in a hydrogen with a positive charge to reflect what I have over here. Okay, so I notice that that ionizable hydrogen, that proton is here on the product side, which means it is found here on the reactant side. So that's my proton that has been passed, okay? Well, the acid, the hydronium ion is going to pass it to this guy, right? So I've established my acid and my base, and then the result on the other side are the conjugates, okay? So acids turn into conjugate bases, and my bases are going to turn into conjugate acids. Okay, amazing. Once again, the acid on either side has the proton that's involved in the transfer. Okay, notice how I've been using the words like, okay, these are the same dudes on both sides, but just now with the absence or presence of an extra proton. This leads to the establishment of something known as a conjugate acid-base pair. A conjugate acid-base pair is a pair of substances, one being on the reactant side and one being on the product side. It's a pair of substances that transform into each other by the gaining or losing of a proton. So here I've boxed off a conjugate acid-base pair. The pair is the guy before he donated his proton and the guy after he donated his proton, okay? Now here's another example of a conjugate acid-base pair. Okay, this girl is the same girl on the reactant side and the product side, except on the product side, she just now has gained a proton from that transfer. Okay, so a conjugate acid-base pair are the two same guys, one from the reactant side, one from the product side, that shows the change in that transfer from the completion of the reaction. So if I look at like a real chemical reaction, here I have an acid and a base, goes to a conjugate acid and a conjugate base. So a conjugate acid-base pair, which will always be two pairs in a chemical reaction equation, will be the two guys that are the exact same except with the presence or absence of the proton, okay? So my acid and its conjugate base, that is one conjugate acid-base pair. Also, my base and its conjugate acid is another conjugate acid-base pair, which is very, very exciting. Okay. Now here's the trick about this, and I'm only going to barely scratch the surface, so this may not mean a lot to you, but I'm going to kind of explain this in a way with why the double-headed arrow maybe is involved in these conjugate acid-base reactions, okay? This says the stronger the acid or base, the weaker its conjugate will be. And the weaker the acid or base is, the stronger its conjugate would be. When you're like, what is even going on here? Well, here, let's pretend here. This is a weak acid, and let's pretend over here this is a weak base. So my reactant side, I have two guys that are weak, okay? This means that my weak acid will turn into a strong conjugate base. This means my weak base will turn into a strong conjugate acid. If either one of these were strong, its conjugate would be weak. So the strength of the conjugate will always be the opposite of whatever the strength is of the original guy. You're like, why do we care about this? Well, looking at this double-headed arrow, this reversible reaction has the ability to run in the reverse direction, okay? Now, depending on what sides are the strong players is going to shift the equilibrium in some way to accommodate for which direction the proton would be preferred to be transferred, okay? So looking at this, these guys are both some weak business over here, which means these guys over here are strong, are probably much more likely to play past the proton, which would favor this reversible or reversed reaction. Y'all are like, oh, okay, this is for future steps for next time chemistry for when we get into equilibrium acid-base systems, which is something to look forward to. Okay, but I really want to unpack and predict how to figure out what a conjugate acid-base pair is. So what we're going to do here is I've given you a selection of acids, and we're going to see if we can come up with its conjugate base, meaning what he would turn into after I've removed one proton, because remember, acids are proton donors, okay? Its conjugate base will be the result of him kicking off or removing from a proton. And yes, that proton will go to somebody else, a base, but we're just looking at the acid, what he's going to turn into. Okay, now you're like, cool, it's just going to be R. Well, keep in mind that proton has a positive one charge. So yes, that hydrogen will be removed, but now I've taken a neutral thing and I've created a negative one charge because I've removed a positive one charge, okay? Here I have nitric acid, right? So nitric acid, I'm going to remove a proton from him. He is now in O2 minus. Oh my goodness, that's super exciting. And then right here we have phosphoric acid. I'm going to remove how many protons? One proton. So that is going to be H2, and it will be PO4 minus. Noticing that each one of these neutral guys now has turned into a negative one charge here, which is really fun. Okay, now kind of spinning it to that mentality that I said strong acids turn into weak conjugates or weak acids turn into strong conjugates, I can actually look at my list of acids that I started with here and be like, are you strong or are you weak? And predict what the strength is of the conjugate that it forms, okay? We know hydrobromic acid is a strong acid. We know nitric acid is a strong acid. We know phosphoric acid, oh, he's not on my list of strong, so he must be weak. That means for my strong guys, the conjugate bases that they will form will be weak bases. And that means for my weak acid, the conjugate base that he will be forming is a strong base. Very exciting. Okay. Here we go. Now we're going to do the opposite of this. I'm still going to create a conjugate acid-base pair, but here I'm going to look at what conjugate acid the base turns into. Remember, according to Bronsted-Lowry, bases are proton acceptors. So that means to figure out, well, what conjugate acid he turns into, I'm just going to add a proton. Not only are you going to add a hydrogen, you have to add that +1 charge, okay? So looking at this, I'm starting off with the nitrate polyatomic ion. If I add a hydrogen and a +1 charge to him, okay, y'all, he's neutral. So this is nitric acid. I've created nitric acid. So this is a conjugate acid-base pair between these two substances. The only difference between the two is the presence or the absence of one proton. Okay, here I have the iodide ion, okay? If I give him a proton, he turns into, look at that, that's hydroiodic acid. And then finally right here, I have HSO3 minus. We'll give him a hydrogen ion, and now he's H2SO3 with a neutral charge. Okay, I can look at all of these acids and identify whether they're strong or weak. Nitric acid and hydroiodic acid are both strong, and sulfurous acid is a weak acid. So the original bases of my strong acids were weak, and the original base of my weak acid that I produced as a conjugate was strong, which is super fun. Okay, so that was my lesson on conjugate acids and bases, okay? Conjugate acid-base reactions are super duper fun. They're also a real fun way for us to be able to play with equilibrium systems when we study acids and bases, but we're not gonna get into that. We're ready to move on to some more simple things, okay? Single replacement acid-metal reactions. Let's see what happens to acids when they react with metals. Y'all, some metals react vigorously with acids to produce hydrogen gas and a salt. Keep in mind, a salt is any general ionic compound that is not an acid or a base, okay? Y'all, these are single replacement reactions that will occur if the metal is more reactive than the hydrogen according to the activity series, okay? Y'all, a metal will replace the hydrogen in the acid if it is above the hydrogen, okay? So we notice hydrogen is actually kind of a little bit closer to the bottom. That is super fine. But if the incoming metal is higher up on the list than hydrogen, he will kick hydrogen out. Remember, he gets the girlfriend in the couple, and hydrogen is now left alone by himself, okay? But if the metal happens to be below hydrogen, we like to think about that as him being less attractive than the hydrogen in the acid, which means they will not kick out hydrogen and the couple will still withstand with the more attractive hydrogen being paired up with the anion. Okay, so here's some picture examples here. I've got aluminum being dropped into an acid, copper being dropped into an acid, iron being dropped into an acid, zinc being dropped into an acid. The presence of bubbles lets me know if this reaction occurs because I will create hydrogen gas from the displacement of my hydrogen. So I'm hoping to see aluminum, iron, and zinc, all three of those that did react to produce hydrogen gas. Hopefully they're all above hydrogen in the activity series, which that looks like exactly what I'm seeing here. Copper, oh, no reaction, which must mean that copper, oh yeah, he's a little bit lower than hydrogen, so we would have no reaction occurring. So here's kind of an example of what that looks like. Y'all, this is a single replacement reaction where I see a single guy, in this case is sodium, and a couple between hydrogen and bromine. If sodium, the metal, is more attractive than hydrogen, meaning higher up, then he will kick out hydrogen to make that hydrogen gas. And a salt, and that specific salt that is made for this reaction is sodium bromide. Okay, so the more attractive single guy will kick out the less attractive hydrogen to make a new couple. So they will get the bromine as their new girlfriend, which is super sad, but that's, chemistry sometimes. Okay, so let's do some practice examples. I kind of want to do some practice examples because this is fun and I actually feel like I want to write. Okay, so we do have some practice examples. I will need my periodic table. Where you at, periodic table? Because I will be looking at my activity series, my who's hot and who's not list, noticing that hydrogen's right here, okay? So let's see. Our first one right here says zinc reacts with hydrochloric acid. You're like, what do I even do here? Okay, first thing we're going to do is we're going to write our reactants, because then we're going to establish that, oh yes, I see a single person and a couple, and then I can be like, oh yeah, single replacement, we know what to do. Okay, so zinc, what is the symbol for zinc? He's by himself. The symbol for zinc is Zn. Yay. Okay, I'm also going to leave a blank in front of zinc because I will come back to balance this. All reaction equations need to be balanced, okay? But he is single, he's by himself. And the couple, the acid that he's going to try to interrupt here, is hydrochloric acid. When writing a formula, hydrochloric acid, which means it is hydrogen paired up with chlorine from the periodic table. Hydrogen always has a +1 charge. Chlorine, according to my periodic table, is a halogen, so he has a -1 charge. So the ratio of ions in hydrochloric acid is 1:1, so I have HCl. Okay, so now we're going to see if this reaction is going to actually occur, which means I got to find my activity series and compare zinc and hydrogen. Okay, zinc and hydrogen, zinc and hydrogen. Here's hydrogen right here. Zinc is, oh, he's higher up. Zinc is prettier, so the prettier option will get the chloride girlfriend right here, which means hydrogen gets kicked out. Oh my gosh, I get kicked out. Remember, when you're writing products, you get rid of any previous subscripts if there were any on the reactant side, okay? Now I put hydrogen off by himself, but the only thing you have to catch is if you are writing a single element and it is one of my diatomic elements, they must come in twos. So this single hydrogen will come in twos. Okay, that means I need to write the new formula between my new couple. It is a couple with zinc and chlorine now, okay? The cation, the positive metal cation, will be written first in the formula. Zinc, what charge does zinc have? What charge does zinc have? Zinc always has a +2 charge. He's one of my transition metals that always has 1 charge and 1 charge only. So that means when I'm pairing zinc up with my chlorine, it is going to be a 1:2 ratio, okay? So it'll be ZnCl2. That just means that 2 chlorides with -1 charges will need to neutralize that 1 zinc with a +2 charge. Okay, so now we get to balance. It looks like to balance, my hydrogens and my chlorine situations are all 2 over on the product side, so I can put a 2 right there. So that's a single replacement reaction. Congratulations. If I put zinc in an acid, it would make bubbles, and that means the reaction has occurred. Okay, next one I have magnesium reacts with sulfuric acid. Okay, so I've got magnesium as my single metal guy. Mg. Amazing. And sulfuric acid is a compound. That acid compound is between, well, it does not start off with hydro. Okay, that means my hydrogen is going to be paired with a polyatomic ion. Well, what polyatomic ion? Ick. Remember, my 8s turn into ick. I ate something icky. So I've got sulfate polyatomic ion, which is SO4 with a -2 charge, which means when I take that +1 from the hydrogen and the -2 from the sulfate ion, I have a 2:1 ratio for my acid, okay? So sulfuric acid is going to be H2 and then SO4. And if you want, for balancing purposes, it's always really nice to keep our polyatomic ions together, but that 2 got put on the hydrogen because of that sulfate having a -2 charge, okay? So now I've done that. I'm like, okay, now magnesium, are you prettier than hydrogen? Let's see. So hydrogen, once again, is down here. Magnesium. Oh, he's significantly prettier. So that means magnesium will kick hydrogen out and will pair up with the girlfriend of sulfate. Okay, so hydrogen, single old hydrogen. Now here's something sneaky. Hydrogen is diatomic, which is why he comes with a 2 when he's single. He does not get a 2 because he had a 2 over here. That is his baggage from his past terrible relationship with sulfate. I would not trust her. She kicked you out to pair up with magnesium. Okay, so you drop subscripts. He gets a 2 just because of coincidence, because he's a diatomic, okay? So that means now my couple is going to be formed between magnesium and sulfate, okay? Magnesium is a group 2 metal right here, which means everybody in a group 2 category will form a charge of a +2. So I have sulfate and magnesium both have charges of 2, so a 2:2 ratio is a 1:1 ratio, which means I have MgSO4, one of each of those. My polyatomic ion, sulfate in parentheses, looks nice because then I can balance it really easily. Okay, so looking at this, it looks like magnesiums are balanced. I have 1 sulfate polyatomic on each side and 2 on, yeah, we are balanced. That is very exciting. Okay, Next up, copper is my metal. Single old copper. Let's see what he can do. Copper reacts with nitric acid. Nitric acid does not start with hydro, so your hydrogen in the acid is going to be paired up with another polyatomic ion. Ick, ick, ick. Remember, I ate something icky, so this polyatomic is nitrate, 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 nitrate. Here we go. NO3 with a -1 charge. Oh my goodness, you guys. Hydrogen with a +1, nitrate with a -1. It is a 1-to-1 ratio, so I have HNO3, okay? Let's see if this reaction will occur. Let's see, copper, copper. Where are you at in comparison to hydrogen on the attractive list? Here's hydrogen. Uh-oh, copper is less attractive. So that means nitrate is like, yeah, no, I'm already paired up with the more attractive oxygen. No, thank you. So no reaction will occur, okay? Copper will not be able to replace that hydrogen. So this would not work out for poor copper. So that was our working through of reminding ourselves how to do single replacement reactions. It's not a big deal. It's just, now the couple that we're looking at for our acid-base unit is a metal, or is an acid that can react with metals if the metals are more attractive on the activity series. Okay, so let's go back to our lesson now that we've learned some good things about my attractiveness of certain metals. We're going to talk about now not single replacement reactions, but double replacement reactions, which we have done before actually a few times. So hopefully this won't be too big of a deal. But when I'm talking about double replacement reactions in my acids and bases, I talk about what's called neutralization reactions. And the little cartoon says, did somebody mix your acid with a base? Because you're a bit salty today. You were like, I don't understand. Well, you will understand. Here we go. Well, what is neutralization? Neutralization reaction is when an acid and a base react to form salt and water. This type of reaction involves the combination of equal molar amounts of the hydrogen ion from the acid and the hydroxide ion from the base to produce a neutral compound of water. So looking at my little example here, I see I have an acid because hello, ionizable hydrogen, right? And I see I have a base because hello, ionizable hydroxide, okay? They double replacement each other, swapping you out partners, which means now I will create a new salt between the discarded sodium ion and the chloride ions to make sodium chloride. That is an example of a salt, any ionic compound, right? And that means hydrogen is going to pair up with hydroxide to make HOH. Guys, HOH is water. I'm writing it that way so you can totally see that it is the result between that ionizable dissociated hydrogen ion and the dissociated hydroxide ion. Okay, so you're like, what is the neutralization? She's saying it's neutral. Yeah, pH of 7 is neutral. Let's talk about why. It all has to do with when I mix a strong acid and a strong base, they dissociate or ionize completely, right? Okay, we know that 100% of that compound will dissociate into its ions. So a strong acid and a strong base, like I have here, hydrochloric acid is a strong acid, sodium hydroxide is a strong base, they will completely neutralize each other and the resulting pH will be 7, okay? So what I'm going to break down here is we're going to go through kind of like our complete ionic equation. You're like, oh my gosh, we're not going to get into that this unit, but we are going to use that concept of creating a complete ionic equation to kind of understand how this neutralization occurs. So yes, 100% of the time, hydrochloric acid is going to break up into its ions. 100% of the time, sodium hydroxide is going to break up into its ions. Okay, this is a soluble salt that I've created here. Sodium chloride will break up into its ions. And then water, liquid water. That's your only molecule in here, okay? Remember, we can cancel off our spectator ions on each side, and the resulting net ionic equation is just the formation of water, which we all know is neutral, okay? So because all of these ions are completely existing, complete 100% dissociation, that is all the chemistry that's happening here, and that pH of the formation of that substance is going to be 7, which is really cool. So what we are establishing here is if I add a strong acid plus a strong base in a neutralization reaction, I will have a pH equal to 7. Okay, but remember, weak acids and bases do not dissociate completely. How much dissociation occurs actually depends on how weak the acid or base is. Not all weak acids and bases are created equally. Some are way weaker than others. Do not worry, we are not going to be responsible for figuring out how weak or how strong a weak acid or a base is. That is for future chemistry courses for you guys to get excited about. But we can predict what the pH value would be if I'm doing neutralization reactions involving one of these weaker substances. So let's think if we had a strong acid. When a strong acid neutralizes a weak base, the resulting pH will be acidic, okay? Meaning the pH will be a number that is less than 7. But when a strong base neutralizes a weak acid, the resulting pH will be basic, okay? And a basic pH is anything greater than 7. You're like, how am I supposed to remember this? This is what I think about, okay? I think about people like getting in a fist fight, okay? Who's going to win the fist fight? The stronger person, right? Well, here, if both guys are strong, it's going to be a tie, right? Nobody's going to win, which means a tie would be a neutral pH. But here, if I have a strong acid trying to fight with a weak base, that strong acid is going to win. So the overall result will be acidic in some way, okay? The strong acid wins. More acidic is going to be the solution. Now, if I have a reaction between a strong base and then a weak acid, that strong base is going to make the solution be more basic, okay? That's the way I remember. And I always circle whoever my strong guys are to where I can visualize, okay, well, what would the resulting pH be? And technically, the strong guy does not make the resulting solution what it is. That is actually, I don't even want to get into it. Technically, it's the weak guy that creates the acidic or basic situation. But that, like I said, that's for future chemistry. Anyway, for us, we're just going to learn the strong guy kind of overtakes and wins. All right, so now let's do some practice equations because this is going to be super fun. But you guys, they're double replacement reactions, so we're not going to be too afraid. But just now we can predict whether the following double replacement reactions between acids and bases, what pH value that would be, whether equal to 7, less than 7, or greater than 7. So let's see. Okay. I have nitric acid and potassium hydroxide reactor. Like, what is even happening here? So I know this is a double replacement reaction because I have two couples. Then we're going to swappity swap partners. Okay. One of the couples is an acid. Yes, acids are a couple between hydrogen and whoever else, right? Potassium hydroxide is another couple. That's a base couple. That is a couple between some cation and the hydroxide polyatomic anion. Okay, so we can write formulas for both of these things. Nitric acid, it's a polyatomic ion containing acid because it does not start off with hydro, okay? Nitric, ick, I ate something icky, so this is going to be nitrate. Okay, so this is going to be between hydrogen ion with the +1 and nitrate. I'm going to have a little bit more space than I had when we were doing these up here to maybe write out a little bit more of my ions that are going to be involved here in here. So nitrate's got a -1 charge. So my formula for nitric acid is HNO3, keeping the parentheses because it'll help with my balancing. And then I have potassium hydroxide. Potassium, he is a +1 charge. And then hydroxide always has a -1. Noticing how I'm putting hydroxide OH in parentheses. Very, very common that you guys get freaked out and do not think that that is all one thing. And if you have to drop down a subscript, a lot of times it does not get represented for both the oxygen and the hydrogen in that polyatomic. Just, I mean, it doesn't matter for this case, but it will maybe for future ones. So K and then OH, 1-to-1 ratio. Okay, so I swappity swap partners. And the purpose of the swappity swap partners is that the cation from one couple is going to pair up with the anion on the other and vice versa. It's even easier when I'm doing these neutralization reactions because you know one of the products is going to be water, okay? And that kind of helps orient you in some way, okay? So hydrogen is now going to pair up with hydroxide, reminding myself of what the charges for the hydrogen ion on the hydroxide is 1-to-1. So I totally have HOH. Y'all, please write water as HOH. Like, that is water. I cannot count that wrong. Yes. And it helps you balance, which is amazing. Okay. So that's my first couple. My next couple is going to be between the nitrate and the potassium. I have to write the positive potassium first because he's the cation. It is a 1-to-1 ratio of both of those. So I have KNO3. Amazing. So it looks like with 1-to-1 ratios all around, we're already balanced, which is great. But now I want you to predict what the pH of the resulting solution would be. Is it going to be neutral, equal to 7? Is it going to be acidic, less than 7? Or will it be basic? Well, let's see. I got to look at my reactants. Is anybody in here strong? Is anybody in here strong? Well, nitric acid is a strong acid. Huh. Uh-oh. Potassium hydroxide is a strong base. Strong and strong, it's going to be a tie, so the pH will be neutral. So what we're going to write over here is we're going to write strong acid plus strong base. pH is equal to 7. Cool. Yay, this is fun. Okay, let's see the next one. Hydrochloric acid and magnesium hydroxide reactor. Like, oh, Okay, so it's an acid, a couple, and magnesium hydroxide, a base, a couple. We're double replacement reaction neutralization between the acid and the base. Hydrochloric acid, that means hydrogen for the acid is paired up with plain old chlorine. Hydrogen has a +1, chlorine has a -1. So my formula for hydrochloric acid is a 1-to-1 ratio, HCl. And then I've got magnesium hydroxide. Magnesium is a group 2 guy. He's got a +2 charge. Keeping in mind, hydroxide always has a -1 charge. So my formula for magnesium hydroxide, making sure I know that hydroxide is a polyatomic, it's going to need those parentheses in this case because I will need 2 total of them to balance out magnesium's +2 charge. And in fact, I don't really want to write these so close to my chemical formula because I want you guys to realize that I'm just writing these charges to kind of establish my mentality of how to create the formula. This formula itself does not have any charges, meaning these guys are not ions typically when I'm writing the balanced molecular equation like I'm doing now. Sorry, that was a lot of talking. Okay, so now I've just written it above the words that let me know what the charges is that I'm dealing with here. Okay, so now I swappity-swap partners, which means hydrogen's now going to pair up with hydroxide. That sounds great. Do not bring subscripts over. I still have hydrogen +1, hydroxide -1. It will still be that 1-to-1 ratio. We'll balance at the end. Do not worry. And then my second couple is going to be between chloride ion and magnesium ion, utilizing their charges, okay? Chloride's got a -1, but magnesium has a +2, so magnesium written first. It'll be MgCl2. I need 2 chlorides to balance out that 1 magnesium. Okay, we do have some balancing to do. I see I have 2 hydroxides on this side and only 1, so how about we put a 2 in front of my water? Well, then that affects the number of hydrogens outside of hydroxide, which means that's going to be 2, which means I have to put a 2 in front of hydrochloric acid, which then gives me 2 chlorines on the reactant side, but that is okay. That is what I have over here. So we are balanced. We look good. We see an acid and a base turn into salt in a water. Okay, so now we got to figure out what the pH is. Do I have anybody here who's strong? Hydrochloric acid is totally one of my strong acids. Magnesium hydroxide. Nope, he's a weak base. Strong acid. That means the resulting solution will be acidic, which means the pH will be less than 7. So we can state here strong acid plus my poor weak base. The pH will be less than 7. Cool. Okay, amazing. Next one. Phosphoric acid and calcium hydroxide react. You're like, phosphoric acid. Well, it doesn't start with hydro, so I'm dealing with the polyatomic ion here. I'm dealing with the phosphate polyatomic ion because it's ick. I ate something icky. Phosphate is PO4 with a -3 charge. Ooh, so that means when I figure out the ratio of the hydrogen to the phosphate in phosphoric acid, I'm going to need 3 hydrogens. H3PO4. Okay, so that's phosphoric acid. And then I have calcium hydroxide. Calcium's group 2. He's got a +2. Hydroxide always got that -1, right? So I will have CaOH2. Total of 2 hydroxides in there, so the parentheses being important. Okay, I have an acid and I have a base, so we're going to swap partners and make a salt and water, which means my water is going to be formed between the hydrogen ion and the hydroxide ion. Do not bring those subscripts over. Hydrogen's got a +1 charge, hydroxide's got a -1 charge. I still have that 1-to-1 ratio. You're like, we're going to balance. Don't freak out. We'll get there. Okay, my second couple to make my salt is going to be between phosphate and calcium. Oh, don't bring any subscripts over. If there were any, we got to look at the original charges. Phosphate with his -3, calcium's with his +2, making sure I write the calcium first. Okay, so I will need 3 calciums to balance out 2 phosphates. In other words, I need a 2 down here because calcium's charge was +2, and I need a 3 down here because phosphate's charge was a -3. So here we go. Oh my gosh, the balancing of it all. I'm like, I hate this so much. Well, let's see what we got going on here. How about, I'm noticing my phosphates. They're kind of making me nervous because I have 2 of them over here and I only have 1 over here. So how about we put 2 there to give us the 2 phosphates? Well, oh my gosh, now how many hydrogens do I have over here? I got 6. Okay, that's not a big deal. Let's put and I'm looking at just the hydrogen that is found outside of the hydroxide. Well, then that means I need to put a 6 here. That will give me the 6 hydrogens that I'm looking at. Well, then that gives me 6 hydroxides. Okay, what number can I put in front of here as a coefficient that when I multiply by the 2 that I see here will give me 6? A 3. You're like, oh my gosh, what am I to do here? That gives me 3 calciums now. Well, y'all, I got 3 over here, so we're feeling good. A little bit, one of a fun one to kind of balance, and that is okay. That is fine. All right, so yes, this is a acid-base neutralization reaction. I take my acid, I have my base, we swappity-swap, we make neutral, or we make water and a salt. Okay, now to see if it is neutral or not, I'm looking at the strength of the acid and the base. Phosphoric acid is actually a weak acid. Calcium hydroxide, let's see, my strong bases are group 1 hydroxides, and out of group 2, my Senor Baca, meaning strontium hydroxide, barium hydroxide, and calcium hydroxide. So this, you guys, totally is a strong base. Oh, that was an aggressive circle. I feel like I'm going to erase that because I want a little bit of space to see what the words are saying on the next question. Okay, so that's my strong base. Okay, weak acid, strong base. Strong base. Strong base is going to win the fist fight, and it's going to make the solution basic. Okay, so we have a strong base plus a weak acid. So the pH of this solution will be basic, and basic is a pH that is greater than 7. Last one. Okay. Sulfuric acid and ammonia hydroxide react. Amazing. Okay, so I've got my acid, sulfuric acid, and I've got my base, ammonium hydroxide. So sulfuric acid, no hydro, so my polyatomic ion, ick, 8. This is sulfate. So the sulfate polyatomic ion is SO4 with a -2 charge. Okay, so I have a compound between hydrogen ion and the sulfate ion, which means my sulfuric acid is H2SO4. Okay. Next up, ammonium hydroxide. You were like, Ammonium is my one-off positively charged polyatomic ion, right? So he's got a +1 charge. So if I'm thinking about it this way, ammonium is NH4 with a +1. That will be paired with my hydroxide, who is a -1. So it is a 1-to-1 ratio of these things, which I'm going to put in parentheses for both of them, even though you don't need them because I have one of each. Typically, you would not see them written with parentheses. You would just see NH4OH, but the balancing would freak me out if I didn't make sure to remind myself that they're all together. Okay, so I've got an acid and a base. We're going to swap and make salt and water. So the hydrogen pairs up with the hydroxide. Do not bring subscripts over. HOH. We're always making HOH. You see, ain't no subscripts here because that is just a 1-to-1 ratio between the hydrogen ion and the hydroxide in the formation of water. Okay, and then that means my second couple that I'm making on the product side, my salt is going to be between sulfate and ammonia, or ammonium. The ammonium ion's positive, so he has to be written first. The sulfate is negative, so he has to be written second. Noticing that sulfate has a -2 charge, ammonium has a +1 charge, so that means I need 2 ammoniums to neutralize that 1 sulfate. Cool. The balancing of it all. Well, it looks like I got, let's see, 2 ammoniums over here and 1 over here. Let's see, we put a 2. Now my ammoniums are balanced. That gives me 2 hydroxides on this side. So I'm going to put a 2 in front of my HOH to give me 2 hydroxides. That also gives me 2 hydrogens, which means, I'm good. Yay, we're balanced. Amazing. Tell me about the pH. What do I got? The strength of the acid and base is what I'm looking at here. Sulfuric acid. Ooh, he's totally strong. This is a strong acid, you guys. Ammonium hydroxide. He is not a group 1 hydroxide, and he is not a Senor Baca hydroxide, meaning strontium, barium, calcium hydroxide. So I've just got a strong acid. Strong acid is going to make the solution acidic, right? So I have a strong acid plus a weak base. Hopefully you guys can see that, which means my pH will be acidic, so it will be less than 7, which is really fun. So y'all, we haven't really totally learned a lot new here at all, besides now that we've done a double replacement reaction, we can then kind of predict what the pH would be just by looking at the strength of the acids and the bases that have gone into it. So here's the kind of summary that we've done today. Yes, we talked about there's more than one way to think about or how to define an acid and a base, which brought us into our first topic of using the Bronsted-Lowry theory or definition of acids and bases as a proton donor for an acid and a proton acceptor to make a base. This allowed for us to look at and investigate conjugate acid-base equations where acids turn into conjugate bases after they've donated their proton, and then bases turn into conjugate acids after they have added their proton to them, okay? So those are acid-base, conjugate acid-base reactions. Then we talked about these single replacement reactions between an acid and a metal, to where the metal can kick out the hydrogen in the acid if it is more attractive or higher up on the activity series, displacing hydrogen to make hydrogen gas in a new couple of salt. So these were the single replacement reactions. And then finally, we reviewed and did some double replacement reactions again. No big deal. And then two couples swapping partners to make two new couples, except the original couples where one was an acid, the other was a base. And when they swapped partners, they created salt and water, or HOH. Depending on the strength of the acids and the bases on the reactant side, I can predict the pH of the resulting solution. So these are some chemical properties of acids and bases.